Kepler's three laws. All planets move in an ellipse around the star where the star is at one focus. The area swept, this is number 2, the area swept by a planet around a star will be the same for equal periods of time. The third one, the time it takes to orbit the star and the average distance from the star to the planet are connected by the following equation. The period squared is proportional to the distance between the star and the planet cubed. So t cubed is proportional to r cubed. So if r is large, t is larger, so it will be slower. In an ellipse, the distance between the star and the planets will vary, so there's an average distance. Let's have a look at these diagrams of an ellipse. So the relationship between the distances have okay, so in this case, a plus b is always the same, it's always a constant. So the distance between one of the focus to the edge of the ellipse and then the distance from the edge of the ellipse to the other focus, when you add those two together, is always a constant. So in this case, a plus b is equal to c plus d. So an ellipse is defined by 2 points, each called a focus f1, f2, which is above. If you take any point on the ellipse, the sum of the distances to the focus points is constant. The major axis is the longest diameter of an ellipse, and the minor axis is the shortest diameter of an ellipse. So here's another diagram. So here the focus is pointing towards the small black dot. The major axis is the longest diameter. The minor axis is the shortest diameter. So the foci lie on the major axis. If you look at the diagram on the left hand side, the ellipse on the left hand side, the foci lie on the major axis, c units from the center, with the equation c squared equals a squared minus b squared. So the definition of eccentricity, the eccentricity E of an ellipse is given by the ratio E is equal to c divided by a, where c is the distance from the center to the focus and a is the distance from the center to the edge of the ellipse at the major axis. Alright, so this is the second Kepler's law. The perihelion, when any other planet is closest to the Sun. The aphelion, when any other planet is furthest from the Sun. So if you remember, aphelion is away, a for away, when any other planet is furthest away from the Sun, and when any other planet is closest to the Sun. Alright, so perihelion just means the point in the orbit of a planet or asteroid or comet at which it is closest to the Sun. Aphelion is the furthest away. So if you look at the diagram, now can you see that the time it takes to go a short distance? So if you look at A, the planet goes around the star very quick because it's closest to the star. If it's far away from the star, it takes longer to go around the ellipse. So here inside in the diagram it says faster when closer to the Sun, slower when further away from the Sun. Because if you are further away, the gravitational attraction is weaker. If you are so if you're closer to the Sun, you have a stronger gravitational attraction. If you're further away, then there is a weak gravitational attraction. So that's why it is faster when you're closer to the Sun, and when you're further away from the Sun, it's slower. That's why the time it takes is longer. That's why you have a longer arc around A, and B, the arc is a lot smaller. And the areas swept are the same. So if you look at here, if you look at the sector, the center, one of the focus, C and D, that sector, the area of that sector is equal to the sector A, B, and one of the focus. So the planet sweeps out equal areas in equal time intervals. The aphelion is further away from the star, and the perihelion is closer to the star. So the area swept is the same. So this the area of the sectors are the same. So if you look at the distance A and B, that is very short, meaning it takes a long time, but it takes a quick time when it's closer to the star at CD. Have a look at this derivation. I will do this on the board later, but you can pause this to have a look.
We're going to derive Kepler's third law. Let's write down Newton's law of gravitation. So F is equal to G m1 m2 over r squared. And you know that the centripetal force is mv squared over r. Let's equate them. So G m1 m2 over r squared is equal to mv squared over r. Well, one of the m's can cancel, and one of the r's cancel, and now you're left with v squared is equal to gm over r. Now let's put, because this is talking about centripetal force and angular speed, we're going to put everything in terms of the period of the planet's motion. So you know that the period is we know that omega is 2 pi over t, so let's put omega equals 2 pi over t, and you know that v is equal to r omega. Okay, so let's square that first. Square that, so that implies that v squared is equal to r squared omega squared. So that means from there you have r squared omega squared equals gm over r. Right, and let's change that to omega squared. So from there to there, you know that omega squared is equal to 4 pi squared over t squared. Put that into there. Now you have r squared 4 pi squared over t squared is equal to gm over r. Cross multiply, so now you have gm t squared is equal to 4 pi squared r cubed. So from this equation you can see that t squared is proportional to r cubed. So t squared is proportional to r cubed, because assuming that the mass is constant, right? So g is a constant, assuming that mass is constant, and 4 pi squared is a constant. So t squared is proportional to r cubed.
So the final equation is t squared is equal to 4 pi squared divided by gm multiplied by r cubed. So therefore t squared is proportional to r cubed. T is the period, g is the gravitational constant, in this case is 6.67 times 10 to the minus 11. Is that correct? Isn't it 10 to the minus 10? No, it's correct, yes. Okay, 6.67 times 10 to the minus 11. R is the distance between the two objects. M is the mass of the object that is being orbited, or in this case, is the one with the higher gravitational field. So it's the one group creating the gravitational field.